Hello, organic chemistry students. We are still in chapter 2. We're getting near the end. And this particular screencast is going to address section 2.9, protic and aprotic solvents. So if you take a look at what happens when we dissolve sodium chloride in water, what occurs is that the ionic compound breaks into ions, and you have the positively charged sodium cation that is surrounded by the negative region of the water molecules like this here. And the chloride ion is surrounded by the partial positive areas of the water molecules like this. Okay, so sodium chloride really does dissolve quite nicely in water. And what we learned last week, the ionic compounds, even though the ionic bonds are really, really strong, they can still have a very high solubility in a polar solvent like water due to the strong solvation set up by the ion to dipole interactions in the solution that results from this. And we see that with sodium chloride. We can dissolve a huge amount of sodium chloride in water. And as an example, we could take 35 grams of sodium chloride and dissolve it in 100 grams of water, and it will dissolve pretty nicely. But if sodium chloride, for the most part, is insoluble in dimethyl sulfoxide, so DMSO is what they call it. And if you take a look at this, you wonder, why is that? And especially when you look at the fact that DMSO does, it is a polar molecule like water is, but why is it not, why is sodium chloride not soluble in it? DMSO, as a matter of fact, has a much greater dipole moment for Debye than that of water, which is only 1.9 Debye, but sodium chloride is not really soluble in it. Okay, and this is a curiosity. Both of these ions are completely solvated by water, however. So all of this to say that there is more to solvation of the solute than the magnitude of the solvent's dipole moment. What we have to consider is steric hindrance. So in class, I'm going to bring a model of DMSO so you can see exactly what steric hindrance looks like. It's much more dramatic if we have a molecule that you can take a look at. The partial positive charge of DMSO is flanked by two very bulky methyl groups. And this makes it difficult for the chloride ion to even approach DMSO's partial positive charge, unlike water. Okay, the methyl groups introduce what is called steric hindrance. And as a result, while the sodium ion, really dissolves quite nicely in DMSO, the chloride ion is not solvated very well. So here's an image of what this whole interaction looks like. So there's your sodium ion. And notice that the partial negative charge here of DMSO, they can all pretty much fit in there and dissociate with this charge, no problem. And we have what? We have about six molecules surrounding it on the planar surface here. But if we look at the chloride ion, do you see these two bulky methyl groups here? They really do, for the most part, not only do they structurally create some problems, but they also electronically shield that partial positive charge. So those groups really do kind of diffuse, the feel of that positive charge by the chloride ion. So that's why the chloride ions really do not, are not solvated in this solution. So steric hindrance really does play a big problem here. So now we're going to look at the difference here between what is a protic and an aprotic solvent. Water is an example of a protic solvent because it possesses a H-bond donor. And solvents like DMSO do not possess H-bond donors. These are called aprotic solvents. Let's go back a couple slides and take a look at that. So if we just look at this molecule here, we see that there is no H-bond donor here at all. Okay, so we would call this solvent an aprotic solvent. Okay, and see the following table of polar protic and aprotic solvents. This table is on page 109 in your textbook. And if we look at the polar protic solvents, these again are all solvents that have H bond donors. We have water, ethanol, and ethanoic acid or acetic acid. This is the acid in vinegar. It's a pretty weak acid. And these all have H bond donors. But if we look at the polar aprotic solvents, we have DMSO here and propanone or acetone. These both look really, really similar, don't they? But in this case, there's a sulfur here where there's a carbon here. These do not have any H bond donors, and NN dimethylformamide, DMF, also does not have any H bond donors, so we would call this an aprotic solvent. So that, for the most part, is all you really have to know on this. Just know that there are other factors to consider when we try to dissolve ionic compounds in solvents. It isn't just, whether the solvent is polar, but steric hindrance plays a role. And also know the impact of whether a polar solvent is protic or aprotic. We'll see you guys in section 2.10, where we will talk about soaps and detergents. You guys have a great rest of the day.